Alright, very good morning to all of you. I welcome you all on YouTube channel of Unacademy's IIT JAM Live. This is your educator Srishti and I teach live on Unacademy's Plus platform in IIT JAM Chemistry category. So today in this particular session we are going to discuss some practice questions on coordination chemistry, which includes practice question from VBT theorem, which includes practice questions from isomerism and electroneutrality principle. So without further delay, so let's start with our practice session. So here you have very first question right there in front of your screen. Very good morning to all of you. Good morning Mosmi, good morning Shruti, good morning Lovely, good morning Dhani, good morning Sambhav, good morning Sonia. I hope my voice is audible and the slide is also clear. Let me know once in comment section so that we can start with our session. Everything is fine, everything is working fine, then definitely we can start with our session. Okay, so this is your very first question in front of your screen. Please apply your all concepts because we have revised each and every point, okay, from coordination chemistry till your VBT theorem. So just make sure you do not hurry with the questions and apply your all concepts, okay, and then give your answers. So this is first question in front of your screen, and in this particular question you have to find out total number of electrons donated by ligands to platinum ion for this complex. Okay, this is your complex given. You need to find out total number of electrons donated. It's an easy question, so all of you please answer this question. You just need to calculate the total number of electrons donated by ligands to platinum ion. Okay. Okay. What about others? Sambhav, Ankit, Mosmi, Lovely going with C. All right. Shruti is also going with C. What about others? Just please answer this question. This one is very fundamental. Yeah, so the answer is definitely option number C. See how this answer is coming. Total number of electrons donated by ligands to platinum ion. Okay, so this is your complex PTEN2Cl6. Okay, and coordination number for this complex is 6. How? Two is this chlorine ligands, okay, and this one is bidentate ligand. So we have two bidentate ligands. So 2 and 1 bidentate ligand has two donating sites. That means 4 coordination number is coming from these two ethylene diamine ligands. Okay. Then we have 2 chlorine ligands. So definitely 2 is coming from here. So total coordination number is 6. If we have 6 coordination number and each ligand donates 2 electron, that means it donates a pair of electron. So 6 coordination number into 2 electrons is equals to 12 electrons, or what we can say 6 pair of electrons. Okay, 6 pair of electrons. So correct answer is definitely option number C. Great. Let's take next question now. This is your complex given. You need to predict the magnetism of this complex. If this complex is diamagnetic or paramagnetic. Okay, you need to just predict the magnetism of this complex. Take your time, plus please give me your correct answers. Okay, just give me a correct answer that if this complex is diamagnetic in nature or paramagnetic in nature. This is cobalt 4 carbonyl ligands. This complex is having -1 charge. Okay. All right. See, in this particular complex, first of all, what we'll do, we'll find out the number of electrons. Okay. So cobalt's oxidation state is, yes, guys, what is the oxidation state of cobalt? Cobalt oxidation state is -1 because this carbon and ligands are neutral in nature. Okay. So cobalt oxidation state is -1 and cobalt this d electrons is D7s2. Okay, cobalt's d electrons is D7s2. So definitely if this is the electronic system and its oxidation state is -1, that means we have d8 electrons and s2. What we have d8 electrons and s2. Okay, so now we have d8 type of system and we have s2. Okay, so 1 2 3 4 5 6 7 8. Okay, and we have two electrons over here. Now we need one vacant s orbital definitely. Okay, without that we cannot hybridize this particular complex. Okay, just now in the morning session we have learned this complex, this concept that we need vacant s orbital, and how we can make this vacant s orbital by pairing these electrons. Okay, and yes, it's a strong field again, so by pairing these electrons we can get converted d10 system. Okay, and once we just pair these two electrons we'll get converted d10 system. Okay, so hybridization for this particular yes, definitely it's a converted d10 system. So hybridization is sp3. Okay, hybridization is sp3 and the compound is tetrahedral. All right, and what you can see over here, now all electrons are paired, so n is equals to 0. Okay, so this compound is diamagnetic in nature. So this is not a true statement always that tetrahedral compounds are always high spin. Okay, Shruti, this is not the correct statement. They can also form paramagnetic compounds, they can also give diamagnetic compounds. Okay, so you cannot say that this one is tetrahedral, so definitely it will just form paramagnetic. Okay, so you can have low spin also and you can have high spin also, so we cannot define like that always tetrahedral compounds are high spin. Okay, see what you can observe over here, these ligands are pairing up, that means it's a converted d10 system. So this is a diamagnetic compound. Okay, this is a diamagnetic compound. All right, I hope this point is clear to all of you. If in case of any doubts, please feel free in the please feel free to ask your doubts in the comment section. Okay, now let's take next question. Very good morning, Neeraj. So this is your next question in front of your screen. What you need to find out, you need to tell which of the following complex is homoleptic. Okay. Okay, see what we have to check over here, Neha. First of all, if we want to check high spin or low spin, first criteria is if pairing is possible or not. Okay, we have to see after pairing if we can get vacant d orbitals or not. See, let's take an example. Okay, let's clear your doubt. If you have d orbitals like this, okay, and we have d8 system and coordination number is equals to 4. Okay, what we have d8 system and coordination number is equals to 4. So that means 1 2 3 4 5 6 7 8. Okay, so this is your system over here. Now what we have to check, if ligands are strong field ligand. Okay, so now we can just pair this electron. Are you getting my point? We can just pair this electron, and once we pair this electron we got this vacant orbital. Okay, we got this vacant orbital. So after pairing of electrons we got this vacant orbital. Okay, so this time this one is your low spin complex. Okay, this one is your low spin complex. Okay, because we have reduced the spin value. Okay, what we have done, we have reduced the spin value. Okay, if I just calculate the spin value in this system, the spin value is equals to 1. How? Half from this, okay, and half from this. So spin value is equals to 1. Okay, spin value is definitely is equals to 1. So now if I just pair this electron, spin value is equals to 0. That means we have reduced the spin value. Okay, so if I can reduce this particular spin value, what I can say that this system is now low spin. Okay, let's take D9 system. Okay, let's take D9 system. So this is how we can have this D9 system. 1 2 3 4 5 6 7 8 9. Okay, now we cannot pair this one electron because there is no vacant space for this pairing. Okay, let's suppose I pair this electron, still I am not getting vacant d orbital. Okay, so there is no need of pairing of this electron. So that means this one is your, in this particular case we cannot define high spin or low spin because there is no space for pairing. Okay, pairing is not allowed over here, so we cannot define high spin or low spin over here, right? But if I have weak free ligand in this particular case, so we cannot do pairing over here, but yes, there's a scope of pairing. So what we can say that yes, this one is your high spin. Okay, where you can have two values of spin. Okay, in this case we can have two values of spin. One is your half and half, that is 1. Okay, and one is your S0. So we can have two possible values of spin. In that case only we can define high spin or low spin. Okay, but in this particular case there is only one value of spin, that is half. Okay, so we cannot define high spin or low spin. Okay, see, now I hope this one is clear to all of you. Okay, right? Okay, so you just in the morning session also you asked this doubt, so I just explained this over here. Fine. All right, so yes, let's get back to this particular question. So what we have to discuss over here, we have to discuss the concept of homoleptic. Okay, what is homoleptic? In which the all ligands are same. Okay, see, in this particular complex pt is connected with six ligands. Okay, so the coordination number is 6 and all 6 ligands are chlorine only. Fine, so this is a homoleptic ligand. Similarly, in this complex all hydrogens are connected with this aluminium. Okay, all hydrides are connected with this aluminium. So this is also a homoleptic complex. Okay, if I talk about this complex, all carbonyls are there. Okay, we have 4 ligands and all carbonyls are there. So this one is also a homoleptic complex. Okay, so yes, this is also correct, this is also correct, and this is also correct. So correct answer is all of these. Okay, I hope this is clear to all of you. Let's take next question over here. Again, a simple question, so we are revising simple questions so that we can take difficult questions in the next session. Okay, so now we have simple questions in this particular session so that we can take next difficult question in next session. Okay, great. Right. So definitely the question is aqueous solution of this complex, okay, upon addition with AgNO3 produces 3 moles of white precipitate. Okay, that means we have 3 ionizable chlorides. Okay, ionizable chlorides. Okay, so compound formula will be CONH3 whole 6 and it's connected with 3 chloride ions. Okay, so this is going to be a compound formula. So CuNH3 6, 3 chloride ions. So if I just add this compound in AgNO3, okay, if I add AgNO3 to this particular compound, so it will react with these ionizable chlorides and it will give us 3 moles of AgCl, that is silver chloride. Okay, and the precipitate color is white. Okay, so now what we need to find out, we need to find out the primary and secondary valency of this particular metal. Okay, so what is primary valency? Primary valency is equals to oxidation state. Okay, primary valency is equals to oxidation state. So now if I want to calculate the oxidation state, this is -3, that means definitely this is +3. Okay, so if this one is your +3, so oxidation state of cobalt is +3, that means this can be our answer and this can be our answer. So I can definitely cancel out these two options. Next, what we have to find out, we have to find out secondary valency. Okay, and now what is secondary valency? Secondary valency is equals to coordination number. So here coordination number is equals to 6. So correct answer is definitely option number first. Okay, well done guys, this is your next question. So FeL4 2 negative, this is your complex where L are your neutral ligands. Okay, make sure these are your neutral ligands. You have to find out the hybridization of this complex. Okay, so if I take, okay, this is our first part. In second part, if L is equals to cyanide, okay, if L is equals to cyanide, then find out the hybridization. These two parts you have to do. Then you have to decide. Okay, cyanide is actually SFL, strong field ligand. Okay, from next session we are going to start with MOT theory. So we are going to revise MOT theory for all compounds, like for heterodiatomic molecules, homodiatomic molecules, then we have coordination compounds and OMC. All MOTs will be discussed in that course. Okay, and after that spectrochemical analysis will also be discussed. So everything will be clear after that course. Then we are going to jump to our CFT and LFT theories. So now all of you please tell me the hybridization in first part and in second part. Okay, let's do this question. So how we have to do this question? See, in this particular question, what we have to do. So this is our iron. Okay, this is our iron, and this L is your neutral ligands. Okay, if L is your neutral ligand, so oxidation state of iron will be -2. Okay, oxidation state of iron will be -2. Okay, that means iron is D6S2, and if the oxidation state is -2, that means it's a D8 system. Okay, so D8S2 system. Okay, we need vacant orbital, so definitely it will be now converted D system. Okay, I hope you can just understand this point, that it's a converted D system. Okay, converted D system. Okay, D system. If you have any doubts in this concept, please do ask me. This is a converted D system. Okay, if this is a converted D system, then definitely the hybridization is going to be sp3d, that means tetrahedral. Okay, now if I talk about second compound, if I take second compound FeCN negative, so iron oxidation state is +2. Okay, iron oxidation state is +2, that means it's D6 system. If it is D6 system, so 1 2 3 4 5. Okay, 1 2 3 4 5 6. Okay, so now in this particular case, cyanide is a strong free ligand. Okay, so it can definitely do pairing of this particular compound. So now Neha, see now what is the concept over here? So we can do pairing. Okay, after doing pairing we can get one d orbital. Okay, we only require one vacant d orbital because coordination number is equals to 4. Okay, so yes, there is a possibility of two different spin values. Okay, one spin value is 1 2 3 4, that means 2. Okay, how it is coming? 4 into half. Okay, so this is one spin value. Okay, and second spin value is if I just pair this particular electron with this electron. Okay, so it will be like 1 2 3 4 5 6. Okay, and this orbital is now vacant, so it can form dsp2. Okay, it can form dsp2 hybridization. So the correct answer for this one is sp3 and for this one is dsp2 hybridization. So now we have two spin values, so this is your low spin compound. Okay, this is your low spin compound. And what about the magnetism? So we have unpaired electrons. Okay, so this is your paramagnetic. Okay, it is not true that always low spin compounds are paramagnetic. It depends on your complex to complex. Okay, this is your low spin because pairing has been done in this particular compound, and it's paramagnetic because you have two unpaired electrons. Okay, so this one is paramagnetic. I hope you got my point. Okay, yeah. So is this question clear to all of you? Any doubts over here? So this is in case of neutral ligands. Okay, the hybridization is sp3, and in case of the cyanide ligands, the hybridization is dsp2. Okay, so that is how we have to do this particular question. Okay, what if I take neutral? Okay, so let's refine this question. So I hope this one is clear. Okay, so let's refine this question. What if I take L is equals to any weak field ligand? Okay, if L is equals to weak field ligand and L is equals to strong field ligand, the condition is L is neutral ligand. Okay, L are neutral ligands. So what can I say over here? This is your converted D10 system, so hybridization will be sp3. Okay, what about this case? Can I say again it's a converted D10 system? Right, so there is no effect of weak field ligand and strong field ligand in this particular case. Can I say that? Yes, guys, can I say that it's again a converted D10 system? So I'll take your doubt after this particular session. Okay, I'll take your doubt after this particular session. Okay, so this one is particularly D10 system and this is also your D10 system. So definitely the hybridization for both these compounds will be sp3. Okay, so I'm giving you other this next question to solve. You can solve this question. Okay, and yeah, anyways it's going to be sp3. Fine, so you can just definitely solve this question, and I'll take your doubts after completing all questions. Okay, so definitely I'll take all your doubts. See, filling is of d electrons. Okay, and d electrons are from metal, so ligands won't affect the filling of electrons. They are only responsible for pairing of electrons and for transference processes and for your converted d10 processes. Okay, this is only the role of your ligands. Rest the electrons are filled according to your metal only. Mridul, how it's option number 3? Mridul, how is option number 3? No, Neha, we cannot say like that. Key neutral ligands are always weak. See, let's take an example of carbonyl. This is a neutral ligand, but this one is strong field ligand. Okay. So in the next course, okay, in the next course, we are going to talk about ligands only. So no worries. Okay, we'll talk about this concept in detail. So after that course, everything will be clear. See, all these questions are level 1 questions. Okay, so if you guys give me good response of level 1 questions, okay, then definitely I'll take level 2 questions. Right now we are more focused on level 1 questions. Okay, so that I can analyze how much you have learned from this particular course. See, The question is, which of the following octahedral complexes do not show geometrical isomers? Okay, so yeah, let's talk about first complex and let's see how much you have revised. Tell me number of geometrical isomers in first complex. Yes guys, how many geometrical isomers can we get in first complex? I'm talking about first option. Just tell me how many geometrical isomers are possible over here. Okay, tell me total stereoisomers, not geometrical isomers, total stereoisomers. Okay. All right. See, in this particular question, this is your complex. Okay. So what can I say over here? We can get FAC and MER. Yes, guys, we can get two geometrical isomers over here, FAC and MER. Okay. It's A3B3 type of formation. So we will have two geometrical isomers, FAC and MER. Okay. So if I talk about FAC, fine. If I talk about FAC, so that means this is cobalt, NH3, NH3, NH3. These red ink represents your NH3. Okay. Then we have three chloride ligands like that. Okay. So now, do we have any plane of symmetry in this particular compound? Yes, tell me, do we have any plane of symmetry? Yes, we do have one. Okay. See, this is how we have plane of symmetry. So if I pass a plane from here, so this is mirror image of this one, this is mirror image of this one. Okay. So this is optically inactive. Now if I talk about meridional isomer, so you have cobalt and you have two ligands opposite to each other 180 degrees. Okay. So definitely this one is also optically inactive. So total stereoisomers will be 2. Okay, that means two geometrical isomers, FAC and MER. There is no optical isomer, only two geometrical isomers. Okay, so this is how we can represent this particular question. Okay, I hope this one is clear to all of you. Now the question is, okay, similarly let's talk about second one. Okay, this is nothing but, this is also coordination number 6. Okay, and you have this like complex. Okay, Ma2B4. Okay, so you'll get cis and trans. You'll definitely have cis and trans. Okay, now if you have cis and trans, okay, so definitely you can form geometrical isomers. Okay, now if I talk about this complex, okay, similarly this one is also your square planar complex, but we can have cis and trans combination, two ammonia ligands opposite to each other, two chloride ligands opposite to each other. This is your transformation. Okay, if two ammonia ligands and two chloride ligands are 90 degrees to each other, this is your cis formation. So yes, we can get geometrical isomers over here. Okay, now let's talk about this complex. Okay, you have three symmetrical bidentate ligands. Okay, you have three symmetrical bidentate ligands like this. Okay, this is your first bidentate ligand, this is your second bidentate ligand, and this one is your third bidentate ligand. Okay, so now there is no possibility of opposite pairs. Okay, there is no possibility of opposite pairs. A is opposite to A. Okay, and it will always remain opposite to A only. So in this particular case, there is no possibility of geometrical isomer. So correct answer is option number 4. Okay, I hope all of you are clear with this concept. Okay, see, theory is very important, questions are important, but before that we have to approach the theory. Okay, so from theory only this concepts should be clear. Okay, that this is how we can write down these opposite pairs and how we can find out the geometrical isomers. Okay, I hope this is clear to all of you. Next is this question. Okay, yeah, we have discussed this question in the previous slide also, but you can just definitely tell me again that is if this compound is paramagnetic or diamagnetic. Or first is this part, second inner orbital complex, outer orbital complex, third one it's a high spin or low spin. Okay, these all three things you have to tell me for this complex. Okay, all right. In morning session only we have discussed this concept. Okay, still some of you are giving me incorrect answers. Okay, just let me know if you have doubt. Okay, see, you have to speak by yourself. Okay, if you have doubt, please do let me know. So let's solve this problem. Okay, in this particular case the oxidation state of iron is -2. Okay, and its configuration is D6s2. That means if I add 2 electrons over here, so it's D8s2. Okay, so that means it's nothing but converted D10 systems. Okay, it's nothing but converted D10 systems. All right, so this one is your converted D10 systems. So what we have to say, see, we have 5 d orbitals like this, 1s and 3p. Okay, so 1 2 3 4 5 6 7 8 9 10. Okay, so it's a converted D10 system. Now what will be the hybridization? Hybridization will be sp3. Okay, hybridization will be sp3. Is this point clear to all of you? Hybridization will be sp3. Okay, so if the hybridization is sp3 and you can see that there is no unpaired electron, so definitely it's diamagnetic in nature. Then next concept is inner orbital or outer orbital. Okay, see, for inner orbital and outer orbital at least you need one d orbital in hybridization. Okay, and there is no d orbital in hybridization, so definitely there is no concept of inner orbital or outer orbital. Okay, so no concept of inner orbital or outer orbital. Next is high spin or low spin value. Okay, see, in this particular case we cannot, we can define this high spin and low spin. Okay, yes, we can define that because these are strong field ligands, so that means these are converted D10 systems. Okay, so yes, there's a concept of a low spin. Okay, so this one is your low spin complex because you have just paired on electrons. Okay, so that's how we are going to define this particular case. Okay, I hope this one is clear to all of you. Yeah, so oxidation state is -2. All right, Shruti, please do not do these type of mistakes. Okay, I hope you are clear with this concept. Okay, so we cannot afford such silly mistakes. Okay, so the oxidation state is -2. Great, so let's take next question here. There is no high spin in this particular case. Okay, guys, there is no high spin or low spin in this particular case. Why? Because only there is D10 system present. Okay, so if there is D10 system present, so always this will be in this particular form. Okay, so there is no concept of high spin and low spin, and there is no concept of inner orbital complex and outer orbital complex. Okay, I hope you all are clear with this concept. Okay, now this point is clear, Dhani. There is no concept of inner orbital and outer orbital. Okay, okay, so the next question is, which of the following is or are inner orbital complex? Okay, All right, fine. In this particular question, see, in this question, let's use our concepts. Okay, what about others? Those who are present in the session? What about others? What's your correct answer? Okay, great. Right, very good, Sambhav, Ankit, Lovely, Sonia, Priyam, Dhani, Aditya, Shruti, Mosmi. Very good, okay? Very good, Nayan. Let's solve this problem now. Okay, so if I calculate, right, the oxidation state of iron, the oxidation state of iron is +2. First point, that means it's a D6 system. Second point, the coordination number is equals to 6. Okay, so now 1 2 3 4 5. Okay, so we have to fill 6 electrons, 1 2 3 4 5 6. Okay, and it's a strong field ligand, so yes, we can do pairing of electrons. Okay, we need two this vacant d orbital, so definitely both these electrons will be paired. Okay, and that's how we are going to get D2sp3 type of hybridization. Okay, so this one is your inner orbital complex. Now let's talk about this complex. Chromium is in +3 oxidation state. Okay, so in +3 case, ammonia are your strong field ligands. Okay, we are going to talk about that in upcoming session. So ammonia are your strong field ligands. So chromium is +3, that means D514S1. So in +3, it will be having D3 type of system. Okay, so that means D3 type of system, 1 2 3. Okay, and there will be two vacant orbitals. So D2sp3 hybridization, again inner orbital complex. Okay, next is this particular complex. So you have manganese in +3 oxidation state. Okay, so it's again D5s2, that means it's D4 system. Okay, so yes, we can pair electrons, it's also D2sp3. Okay, so now you guys tell me about first complex, if it's a high spin or low spin. Okay, just tell me about all complexes. Just tell me the spin nature of all complexes. Again, first, second and third, it's a high spin or low spin. It's a high spin or low spin, all complexes. Okay, first, second and third. Just tell about these three complexes. It's a high spin or low spin. Okay, on November 3rd, we are going to have one special class on Unacademy platform. Okay, in this particular special class, we are going to discuss micro notes. Okay, and followed by the practice sessions. So we are going to take three chapters in this particular series. Okay, first chapter is chemical equilibrium, second chapter is ionic equilibrium, and third one is phase equilibrium. Okay, so first we are going to discuss micro notes on these chapters, then we are going to practice questions on these chapters. Okay, so it's starting from November 3rd. If you want to enroll in this particular course, it's very beneficial for 21 aspirants. So you can find the link in the description box. Okay, you'll find the link over here. And if you want to join live classes on Plus platform, okay, so this is my referral code, that is SBATRA. You can definitely use this referral code for additional 10% discount. Okay, so we are only 3 months just before from our examination, so right now it's the perfect time that you should enroll yourself in these revision courses. Okay, so our new revision course is also starting from November 1st, so you can enroll in that particular revision course also. If you want to ask any queries, or if you have any queries related to these revision courses, you can definitely message me on Unacademy app. Okay, or you'll find the Telegram channel link in the description box. You can also message me from there. All right, so let's discuss this question now. Okay, all right, see, if I talk about first complex, okay, if I talk about first complex, so there is pairing. Okay, if there is pairing and we have paired the electron, so this one is low spin. Okay, so first complex is low spin. In second complex, okay, see, there is no concept of pairing. Okay, there is no concept of pairing because we have two vacant orbitals. Okay, so there is no concept of pairing in second complex. Concept of pairing, no concept of pairing. Okay, so there is no concept of high spin or low spin. If I talk for third, if I take third complex, so yes, there's a concept for pairing, so definitely this is also low spin. Okay, so first one is low spin, third one is low spin, First one is your diamagnetic compound, okay. Second one is your paramagnetic compound, and third one is also your paramagnetic compound. So there is no relation of low spin with diamagnetism, and there is no relation of high spin with paramagnetism, okay. I hope all of you are clear with these concepts, okay. These are very important concepts. So next is this question, okay. The zero magnetic moment of octahedral compound, that is your K2NiF6, is due to, these are four options given for this question. You need to find out the correct reason for zero magnetic moment of this octahedral compound. Okay, second one, see Mridul, in the second case you have three electrons, okay. You have three electrons, so there is no need of pairing because you need two vacant orbitals, and that are already present in this particular case, okay. So there is no need of pairing, there is no necessity of pairing, so we cannot define high spin or low spin in this particular complex, okay. So there is no concept of high spin or low spin, because that only comes when you have two possible spin values. See, there is only one possible case of spin value, that is 3 by 2, okay. You have three unpaired electrons, and you have three unpaired electrons, each one is having half of spin value, so spin value is 3 by 2, okay. So definitely if spin value is 3 by 2, there is no possible case of other spin value. So this case, in this particular case, we cannot define high spin or low spin, okay. Yeah. Okay, Dhani, you are present on plus, no? So just complete the detailed version of equilibrium. Then you can watch this class. Okay, we can just complete the detailed version of equilibrium. Then you can watch this class. Okay, if you have time, see if your syllabus is going good, okay, and you have time to just complete equilibrium in detailed form, then definitely you can complete it. Otherwise you can also watch the micro notes section, and you can prepare your micro notes, okay. If you'll find time after some months, okay, you can cover it in detailed form. Otherwise these micro notes will be sufficient for you to practice questions from equilibrium. All right. Okay, so in this particular question, yes, the compound is K2NiF6. Okay, so this is your NiF6 2 negative. All right, so oxidation state over here is +4. So nickel is having +4 oxidation state. Okay, although this fluoride ligands are weak field ligand. Okay, but due to this +4 oxidation state of nickel, this is a low spin complex. Okay, and we have pairing in this particular complex. So this was the correct answer for this. This is low spin D6Ni4 complex. Okay, I hope this is clear. Let's take next question now. Which of the following will show optical activity? All these are level 1 questions, okay. So now you're giving me good responses. Actually for level 1 questions, so soon I'll plan a level 2 question YouTube session, okay, for coordination chemistry. But as soon as we are completing the topic of coordination chemistry, I'll take practice questions on it, okay. So we'll be practicing questions on a daily basis now for this particular super 100 batch course, okay. Why zero magnetic moment in particular case? See, Ni4, okay, Ni plus 4. Okay, where in this question it's written that it's having zero magnetic moment. Okay, yeah, it's written zero magnetic moment. So you have Ni plus 4. Okay, so Ni means D8S2 system. So plus 4 means it's a D6 system. Okay, so 1 2 3 4 5. All right, Sonia, 1 2 3 4 5 6. Okay, so that is how it has zero magnetic moment. Okay, now it's clear. No, you can see from this structure, okay, that this way it is having zero magnetic moment, okay. Yeah, so let's solve this problem. Which of the following will show optical activity? See, whenever you see trans cases and optical active compounds, you can directly cancel out this case, okay, because trans will always have at least one plane of symmetry, okay, which bisects your plane of molecule and reflecting your two trans molecules, okay. So yes, this one is our optically inactive. If I talk about this case, this is also optically inactive. Why? Because all ligands are same, and definitely you'll find one at least pair 180 degrees to each other, okay. So this is also optically inactive. Correct answer is option number A. Okay, now you have this question in front of your screen. You have to tell the hybridization for this complex. Yes, all will act as plus strong free ligands and plus 4. Okay, if you have high oxidation state, all ligands will behave as the strong free ligand in your higher oxidation states. So you need to tell the hybridization for this complex. Okay, all right. Okay, what about others? All right, you need to tell hybridization for this complex. See, in this particular question, what we have to see. All right, guys, just tell me oxidation state of iron. All of you, please let me know oxidation state of iron in this particular complex. What is the oxidation state of iron in this particular complex? Okay, and what is this particular complex? Okay, can I say it's nothing but brown ring complex? Yes, everyone, can I say that it's nothing but brown ring complex? Okay, yeah. So what is the oxidation state of iron in brown ring complex? All of you, just tell me what is the oxidation state of iron in brown ring complex. Okay, all right. What about others? All right. Rajendra says 3, Mridul 3, Dhani 1. All right. Priyam 1, Sambhav 1. Okay. What about others? Yes, everyone, those who are present, just tell me the oxidation state of this iron and brown ring complex. Yes, +1, +1. Okay, great. So the oxidation state in brown ring complex is +1, not +2. Okay. So this nitrogen ion is present in NO plus form. Okay. So that means X minus 1 is equals to 2. Okay. This one is +1. So X plus 1 is equals to 2. So X is equals to +1. Okay. So this iron is actually present in +1 oxidation state. So oxidation state of iron is +1. So it's a D6S2 system. Okay. +1 means D5S7 S2 system. Okay. Or I can say S1D6 system. Okay, this is how we are going to write down this case. Now we have 6 electrons in D. Okay, 6 electrons in D. 1 2 3 4 5 6. Okay, we have 6 electrons in D and 1 electron in S. Okay, so what will happen? Definitely this will pair. Okay, this will definitely pair with this particular electron. So what will happen? You will have now this d orbital vacant, and you will have 3 p orbitals like this. Okay, and 2 d orbitals. So hybridization in this particular case is sp3d2. Okay, hybridization in this particular case is sp3d2. Okay, so this is how we are going to write down the hybridization. Okay, now tell me if it's a high spin complex or low spin. What about the spin nature? It's a high spin complex or low spin? It's a high spin complex or low spin? Okay. And what will be the magnetic moment? Just find out the magnetic moment also. See, definitely this electron will be paired. Okay, because we need vacant orbital. All right, we need vacant orbital, so this will be paired obviously. Okay, so two hybridizations are possible for octahedral, d2sp3 and sp3d2. Okay, so yes, it will be definitely paired. Okay, so yeah, the magnetic moment will be somewhere around 3 because you have 3 unpaired electrons and n plus 2. Okay, that is how we are going to solve this particular question. Okay, I hope this is clear to all of you. Let's take next question. Okay, which of the following will have greatest molar conductance at infinite dilution? Okay, let's make more. Let us just take this question to next level. Okay, first one is this question only. Second one is you need to calculate. Let's say you need to calculate n factor. Okay, you need to calculate n factor of all compounds. Okay, and second part is you need to calculate van 't Hoff factor for all compounds. Okay, so just tell me, first part is definitely, this is your first part, the question. Then you have second part, you need to calculate n factor for all compounds. Third part is you need to calculate van 't Hoff factor for all compounds. Okay, this is your question. Okay, so this is your question. First part, which will have greatest molar conductivity, or you write down order for conductance. Okay, just tell me order of molar conductance at infinite dilution. You have 4 options for that. Okay, just tell me order of molar conductance. First part, second part, order of n factor. Okay, order of n factor. Okay, decreasing order, you have to tell decreasing order. Okay, in first part you have to tell decreasing order of molar conductance, second decreasing order of n factor, third one is decreasing order of I factor, that is your Van 't Hoff factor. Okay, so this is the question you need to tell. Just write down the orders, okay? Decreasing order of molar conductance, decreasing order of N factor, decreasing order of Van 't Hoff factor. Okay, very good, Sambhav. What about others? Just write down the correct order. Okay. See, can I relate molar conductance with Van 't Hoff factor? Can I say that, guys, molar conductance is directly proportional to Van 't Hoff factor? Yes or no? Can I say that molar conductance is directly proportional to Van 't Hoff factor? Yes or no? Just tell me, can I say that molar conductance is directly proportional to Van 't Hoff factor? Okay, definitely we can say that molar conductance is directly proportional to Van 't Hoff's factor. Okay, so yes, what the order of molar conductance and the order of Van 't Hoff factor will be definitely same. Okay, so now let's write down the molar conductance order. If this is 1 2 3 4, okay, so molar conductance order will be 4. All right, then you'll have first, okay, then you'll have second, and then third. Okay, this is your molar conductance order. Similarly, Van 't Hoff order will be same, 4 1 2 3. Okay, this is your Van 't Hoff order. Now let's write down N factor. Okay, N factor for first compound will be 3. Okay, N factor for second compound will be 2 only. N factor for third compound is like 0, you can consider it like 0. Okay, and N factor for this compound is 4. Okay, so correct order of N factor will be 4 1. Okay, then you'll have 2 and 3. This is how we are going to write down the correct order. Okay, 4 1 2 3. I hope this question is clear to all of you. This is your order of N factor, this is order of molar conductance, and this is order of your Van 't Hoff's factor. Okay, great. So let's do next question now. In case of any doubts, please do let me know in the comment section. Okay, this is your next question. How many optical isomers are possible for this complex? Okay, where M is dsp2 hybridized. Okay, Kishore is saying going with 2, Shalini 3, Mridul 4, Nayan 3, Sambhav D, Dhani 0. All right. Okay, lovely 4. Okay, what about others? Okay, all right. All right. Okay, great. See, in this particular question, we need to find out optical isomers. Okay, see, optical isomers. So it's a square planar complex. Okay, and all ligands are monodentate. There is no concept of chirality over here. So correct answer is 0. Okay, correct answer is definitely 0. This is our next question. Okay, N the N is forming a complex with your glycine ligands, okay, which shows two stereoisomers. Okay, it shows two stereoisomers. You need to tell the correct reason for that stereoisomerism. Okay, is it your are two isomers your geometrical isomers or optical isomers, or it's not, the isomers are actually not possible. Okay, or both 1 and 2. Okay, this is your question. Okay. All right. Fine. Okay. Now you guys just tell me about glycine ligand. Okay. Is it a symmetrical ligand or unsymmetrical ligand? Okay. Is it a symmetrical ligand or unsymmetrical ligand? If I draw glycine ligand, okay, you have CO minus over here, you have carbon and you have NH3. Okay. Just tell me, is it a symmetrical ligand or this one is your unsymmetrical ligand? Okay. Tell me, yes, definitely this one. Okay, this one is your symmetrical or it's not symmetrical. Okay, it's symmetrical or unsymmetrical ligand. Okay, this ligand is definitely unsymmetrical ligand. Okay, this is your unsymmetrical ligand. Okay, if this is your unsymmetrical ligand, then definitely can I write M which is coordinated with AB2? Yes or no? Can I write like that, M which is coordinated with AB2? Okay, because it's a unsymmetrical ligand. So yes, what we can form, see, this is AB one ligand. Okay, this is AB second ligand. Okay, so opposite pair is A opposite to B and B opposite to A. What we can form, we can form one type of geometrical isomerism also, in which A is opposite to A and B is opposite to B. Okay, so yes, definitely it shows geometrical isomerism, but there is no concept of optical isomerism over here, because this one is square planar complex. Okay, and there will be always one plane of symmetry if there is no concept of chirality in square planar complexes. Okay, so this one is optically inactive, but it will give us geometrical isomers. Okay, so correct answer is option number A. Is this point clear, Sambhav? Correct answer is definitely option number A. Okay, Sambhav, lovely. Shruti, this one is clear. I hope this is clear to all of you. Okay, let's take next question now, and this is your next question. The complex compound bearing square planar geometry. Okay, just to use morning's class concept. Okay, if you are clear with that first flow chart, okay, that in this particular class we have just drew, so you will be clear with this question. Okay, just remember that first flow chart, okay, in which we have written the D configurations and the possibilities of tetrahedral and square planar complexes. Okay, so without any doubts, you should give me correct answer in 5 seconds. Actually, you can solve this question in 5 seconds. If you are clear with your concept, you can solve this question in 5 seconds. There is no need to write down the electronic structures and there is no need to fill electrons. Okay, so just you have 5 seconds. All of you, please give your answers. Okay, the complex compound bearing square planar complexes. Okay, see, this is the beauty of inorganic chemistry. Okay, either you know the answer or you do not know the answer. Okay, this way you can save your time for physical questions, for organic questions. Okay, so if you are clear with your concept, you can actually save your time. Okay, just build this ability to start solving questions in less time from inorganic section. Okay, so for that you need better hold on your concepts. Okay, so just focus on your concepts. Yes, definitely. The correct answer is option number 2. How? See, this is Mn, okay, and Mn electronic configuration cannot form square planar complexes. If I talk about Z0 to D7 system, okay, they generally form your tetrahedral complexes, and if I talk about D8, D7 and D9 system, they form your square planar complexes, and that too even with your strong field ligand. Okay, so yes, I can cancel out this option without any doubts, this option without any doubts. Okay, now I am left with this option and with this option. Okay, see, in this particular case, this one is converted D10 system. Okay, so this is one is sp3 hybridized. In this particular case, it's Ni plus 2, that means D8 system. If this is a D8 system, then definitely what we can say that there's a possibility of square planar complexes with help of your cyanide ligands. Okay, so correct answer is definitely option number 2. I hope you all are clear with this concept. Okay, next is this question. You have two compounds, compound A and compound B. You need to tell hybridization for both cases, as well as you need to predict their magnetism character. Okay, so this is your question. Yeah, okay, you should actually just find the answer just in 5 seconds. Okay, so this is the beauty of inorganic chemistry. So make sure you are revising your concepts on a daily basis. Okay, so this way actually you can save your time for physical and organic questions. Okay. All right. See, in this particular complex, the oxidation state is +2. The oxidation state is +2 over here. Fine. So this is your D7 system. This is also your D7 system. Okay. Coordination number is 4 in this D7 system. So what I'll do, I'll fill the electrons. Okay. I'll fill up the electrons 1, 2, 3, 4, 5, 6, 7. Okay. So 5 and 6 and 7. So definitely there is no possibility of pairing over here because these are weak field ligand. So hybridization will be sp3. Okay, and in this particular case, there's definitely a the pairing is actually possible. Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, so this pairing is possible. All right, this pairing is possible, and now you will be left with one electron. Okay, this pairing is possible, and now you will be left with one electron. So what will happen? Okay, so what will happen this way you'll get okay, dsp2 type of configuration. Yes, definitely you'll get dsp2 type of configuration, and this is going to be a paramagnetic, and this one is also your paramagnetic compound. Okay, great. One second, last to last compound, optical isomerism. How it will be optical isomerism, Dhani, if you have plane of symmetries? So how it will be optical isomerism? Ma'am, pairing never happens in tetrahedral complexes. Yes, yes, you are correct, pairing never happens in tetrahedral complexes, but uh, we cannot define like high spin or low spin. Okay, it's possible that pairing will happen. Okay, when it's a converted d10 system. Okay, in that case there's a possibility of pairing. Okay, so pairing is actually happening in case of converted d10 system, and that case also is your sp3 hybridized. Okay, so yes, pairing never happens forcefully, pairing never happens. Okay, but yes, you can have diamagnetic compounds. Okay, so this is like we can, it's not compulsory that in tetrahedral compounds you will always get high spin. Okay, there's a possibility of low spin also in tetrahedral compounds, just like we discussed previous questions, d10 system. Okay, that's nothing but your low spin. Okay, that's nothing but your low spin type of complexes. Okay, fine, let's take next question now, and this is our next question. See, due to unsymmetrical ligand, okay, still the compound is planar. You're getting my point? Still the compound is planar. So yes, definitely there will be a planar symmetry. Okay. Yes, unsymmetry is there, but the compound is planar. All right. The ligand is not chiral. Fine. Yes, it's a rare case, Shruti. Okay, it's a rare case, but square planar complexes are possible for D7, but the abundance is very less. Okay, it's a rare case, but yes, sometimes we can observe a D7 system for square planar complexes. Okay, yeah, the correct answer is ionization isomer. See, you have chloride, bromide, and chloride. So correct answer is ionization isomers. Great. Let's take next question. This is your next question. Okay. Yeah, it's very easy question. Okay, just the statements are a little bit lengthy, but the question is very easy. Okay, correct answer is option number A. Correct answer is option number A. Right? I don't think so. There's need of explaining this question. Okay, let's take next question. Which of the following do not exist on the basis of electroneutrality principle? Okay, you have to apply electroneutrality principle and you have to tell the stability of these compounds. Okay, which of the following do not exist on basis of electroneutrality principle? Okay. Fine. All right, guys, let's start solving this question. So in this particular question, nickel's oxidation state is +4. Okay. See, in this particular case, nickel oxidation state is +4. Okay. So if oxidation state is +4 and in nickel we have D8S2 system. Okay, we have D8S2 and oxidation state is +4. That means it's a D6 system. So we have 6 electrons and 6 ligands. Okay, that means we have how many charges coming from ligand? We can have -1 charge from ligands. So we have -6 charge. Is this point clear to all of you? We have -6 charge from ligands. Okay, so all these ligands are giving us right, -1 charge. So we can have -6 charge from these ligands. Okay, then what we can say? We can say definitely this one is nickel +2. Okay, in this particular case it's nickel -4. See, nickel is in -4. Okay, and in this particular case cobalt is in +3 state. Okay, so cobalt is in +3 state. See, -4, just look at this concept. Okay, it's -4, so it's not possible. The correct answer is option number C. Okay, -4 charge is not possible. Okay, it is actually very unstable compound. In this particular case the charge is approximately equals to 0. In this case also you have fluoride ligand, so it's most electronegative element, so it will be neutralized by this fluoride ligands. In this particular case it's +3. Okay, CuCl6 -2 is not existing. That is true, but here the oxidation state has been increased. Okay, so we have increased this oxidation state from +2 to +3. Okay, so then in that case this compound exists. Okay, so correct answer is only option number C. Fine, correct answer is only option number C. All right, is this point clear to Kishore? Right, is this point clear to Mridul, Sonia, Sambhav, Mosmi? Right, this question is clear that how correct answer is option number C. Okay, only option number C is your correct answer. This is not MSQ question, this is MCQ question. Okay, so you have to answer according to that. Okay, let's take next question, and this is your next question. But ma'am, nickel has 6 bonds. Nickel can form 6 bonds. Okay, nickel can form 6 bonds. Here in this particular case, nickel is in +4 oxidation state. Okay, so yes, in +2 oxidation state. See, if this compound would have been NiCl 6 NiCl6 4 negative. Okay, if let's suppose this is your compound. Okay, that means the oxidation state is +2. Then this is not existing. Okay, this is unstable according to electroneutrality principle, because CuCl6 2 minus is not existing. Okay, this one is not existing, so this compound won't exist. Okay, but in this particular compound you have nickel in +4 oxidation state. Okay, which is giving approximately 0 charge on nickel. So according to electroneutrality principle, yes, this compound exists. Okay, great. CuCl6 4 minus. Okay, this compound is not existing. Okay, copper in +2 oxidation state, forming 6 bonds with your chloride ligands. Okay, now it's clear, Mosmi. Any doubts? Any further doubts for this question? Any one of you is having doubt on this question? Just let me know if you have doubts. Okay, great. Fine. So number of moles of ions produced by complete dissociation of 1 mole of Mohr's salts. Okay. What is Mohr's salts? Okay. This is one addition compound. Fine. And it's classified under double salts. Okay. So compound, this formula for Mohr's salt is you have ammonia. Okay. 2 ligands for that. Then you have FeSO4. All right, you have FeSO4 dot 6 moles of water of crystallization. Now if I dissolve this water, if I dissolve this compound in water, I'll get 2 ammonia ligands. Okay, 2 ammonium ions, 1 Fe2 plus ion, all right, and 1 sulfate, 2 sulfate ions. Okay, so 2 plus 2 4, 4 plus 1 5. Okay, so I'll get 5 ions in water. So correct answer is option number C. Okay, so this is your double salt. Okay, not coordination compound. So you have to learn the formulas of double salt, like you have potash alum. Okay, you have carnallite. Just make sure you learn formulas of some basic double salts. Okay, let's take next question. Which orbitals do not participate in hybridization for this complex? Yeah, ferrous ammonium sulfate. Okay. Next is this question: which orbitals do not participate in hybridization of copper ammonium complex? Yes, definitely the correct answer is option number C, because this one is, okay, this is +2 oxidation state. So definitely if I write down the complex C, it's like D9 system. Okay, so it's like D9 D9S2. Okay, and it's +2, it's D9 system. So 1 2 3 4, and then you have 5 6 7 8 9. Okay, so in +2 oxidation state, ammonia is a weak free ligand. So this is your sp3 hybridized compound. Okay, tetrahedral one. So in case of these compounds, you have py, right? You have py, pz, and this okay. Before that, you guys tell me what is the hybridization of this particular compound. Okay, before just telling me what is the before just going to the answer, just tell me the hybridization of this particular compound and geometry of this particular compound. If it's a tetrahedral or it's a square planar compound. Copper nitrate is tetrahedral or square planar compound. Just tell me that. Okay. Yes, definitely it's DsP2 compound. Okay, so this one is your DsP2 compound. So due to transference of electron. Okay, or what should I say? What should I say over here? This compound is like this. Okay, it's a D9 system. Fine, it's a D9 system. Today only I think we have discussed this compound. Yes, guys, it's a D9 system, coordination number. It's a D9 system, coordination number 4. Okay, it's a D9 system, coordination number 4. So 1 2 3 4 and 5. Okay, so this one is a weak free ligand in +2 oxidation state. Okay, in +3 oxidation state this is strong, but in +2 oxidation state this one is weak field ligand. Okay, so due to one electron exchange, this is how we are going to solve this particular question. Okay, so finally the hybridization will be sp3d. Okay, the hybridization will be sp2d. So correct answer is pz orbital. Fine. The correct answer is PZ orbital. Let's take next question now. The correct answer is PZ orbital. Okay. Right. sp2d is the hybridization, not dsp2. You're getting my point. Okay. Lovely. You're getting my point, Chetan. All of you, those who have concluded this dsp2 hybridization, it is not dsp2, it is sp2d. Okay. In morning session only we have discussed this concept, because this one is your NH3 ligand, and it's a D9 system. Okay, it's a D9 system like this. Okay, see, we have D9 electrons like this. Okay, 1 2 3 4 5 6 7 8 9. Okay, so there is no concept of transference over here. So this is like 3, and we have 1 d orbital. Okay, so it's like sp3d. Fine. This point is clear to all of you. Just let me know. This is sp2d complex. Okay, not sp3. Fine. So correct answer is sp2d, and the answer over here is pz orbital. Fine. I hope this is clear to all of you. Any doubts over here? Let's take next question now. Yes, definitely we can see. No. See, okay, I got your doubt, Shruti. Okay, this one is actually genuine doubt, so I would like to explain that. See, if I take D9 systems, okay, this one is actually very genuine doubt. Let's take Shruti's doubt. See, in this particular case, if I talk about this complex, okay, this complex is copper, which is in +2 oxidation state. Okay, if copper is in +2 oxidation state, that means we have 5d orbitals like this. Okay, and the oxidation state is +2, so it's like D9 system. If it's D9 system, so 1 2 3 4 5 6 7 8 and 9. Okay, so now you are left with one electron. Okay, see, if this compound is very reactive. Okay, see, if I say this compound is very reactive, so that means from copper, okay, +2, it will go to copper +3 very readily. Okay, this process is very easy. Then only we can say that this compound is very reactive. Yes or no? Those who are present in this session, just tell me if this reaction is feasible. If E naught potential from +2 to +3 is very high, or it's in positive magnitude, then only we can say that this reaction is very reactive. But this is not the case. Okay, this is not the case. That's why we concluded that there is no process of transference. Okay, if there is process of transference, then this copper +2 can definitely convert to copper +3. Okay, and this is not observed. Okay, this process is not observed yet, that copper +2 is going to copper +3. Okay, so there is no process of transference over here, so we cannot say that this compound is very reactive. You got my point, Shruti? So we cannot say that this compound is very reactive. Okay, it is not having high oxidizing potential value. Okay, it's not having high oxidation potential value. So the correct hybridization over here will be sp2d, not sp3. Okay, the correct hybridization is sp2d, but this is not reactive compound. Okay, this is not reactive compound because there is no process of transference. If there is process of transference, then only we can say that this compound is reactive. And you can see that there is no existence of copper +3 oxidation state. Okay, so that means that this compound is not reactive, but the oxidation state is +2, and the hybridization is sp2d. Okay, yes, its hybridization is sp2d. All right, guys, let's take next question now, and this is your next question. Can we say all D9 systems are sp2 hybridized? See, it happens only in coordination number 4. Okay, it happens only in coordination number 4. If in coordination number 4 we are talking D9 systems, okay, we are talking with respect to D9 systems in presence of weak field ligand, okay, the hybridization is sp3. In presence of strong field ligand, we can say that the hybridization is sp2d. Okay, let's do this question now. All of you please give your answers for this question. Yeah, for square planar complexes we have to check ligands also. If the ligand is actually it's very weak field ligand, so we can say it will form sp3 hybridization. If the ligand is strong, then only we can say that this hybridization is sp2d. Okay, why don't D10 compounds undergo sp2 hybridization? All right, see, in this particular case, see, all electrons are actually paired. Okay, all electrons are actually paired, so it all depends on your, in this particular case it's a D10 system. Okay, so yes, your doubt is actually valid, why D10 systems are not forming your sp2 sp2d hybridized the structures, but it only forms sp3 hybridized structure. It all depends on your stability. Okay, see, it all matters. See, yeah, so how we can explain this concept on the basis of CFSE. See, Sambhav, okay, on the basis of CFSE, okay, yes, on the basis of CFSE, yeah, right, Prem, we can say that on the basis of CFSE, this CFSE is 0, so yes, definitely we can say, if I talk about high CFSE, then I can convert tetrahedral structures to square planar structures. Okay, if I talk about high CFSE, then I can convert tetrahedral structures to square planar structures. But in this particular case, the CFSE is actually 0. Okay, so that's why this structure is dominating. Okay, that is why this structure is dominating. Whereas in copper plus 2 state, okay, this goes to your John Taylor distortion. Yes or no? Copper plus 2 goes to your John Taylor distortion. So due to distortion in this particular compound, okay, so that's why we are having this type of structure. Okay, I'm going to come to all of your doubts. Okay, in whenever we'll be discussing this theory portion, I'm going to come to your doubts. Okay, let's take this question. Yes, the magnetic moment is 2.83. Okay, so you'll be having 2 unpaired electrons. Okay, you'll be having 2 unpaired electrons in this particular case. Okay, I hope this point is clear to all of you. Fine, let's take next question, and this is our next question. Okay, this one's very easy, we have already discussed that. So nickel carbonyl 4 complex, is it diamagnetic or paramagnetic? This one's easy, right? This is diamagnetic or paramagnetic? Yeah, so this is your diamagnetic compound. Okay, this is your diamagnetic compound. Great. Okay, so yeah, so this is all about this particular practice session. Fine, so if you have any doubts over here, or if you have any doubts regarding to Unacademy platform or plus subscription, you can definitely message me on Unacademy's app. Okay, so I'll see you with next session. Okay, so in the next class we are going to start with our MOT theory. Okay, in the super 100 batch course we are going to start with our MOT theory. So you also can take Unacademy's plus subscription if you want to study from live classes. Okay, so this is my referral code, you can just definitely use this referral code. Okay, I'll see you in the next class. Take care everyone. Bye bye. Have a good day.